Welcome to this presentation on vibration and noise control, specifically focusing on the crucial aspect of managing noise at its source, along its path and receiver. This forms the core of noise control measure in our course. Over the next few slides, we will delve into effective strategies and techniques to mitigate unwanted noise and vibration in various engineering applications. I am Sendamrai Kannan, Associate Professor from the Department of Mechanical Engineering, SVC. Building upon our introduction, this fundamental concepts underpinning effective noise control. At its heart, noise control is a systematic process involving several key actions. First and foremost, it's about prioritizing and tackling the most immediate noise related risk. Following this crucial step, we move on to identifying possible methods and critically assessing the reduction levels that can be realistically achieved by implementing a combination of control measures. Effective noise control also necessitates clearly assigning responsibilities for the implementation and maintenance of these measures. Finally, a vital aspect is monitoring the implemented controls and their ongoing performance to ensure their continued effectiveness. We are exploring the fundamental strategies for managing and reducing noise exposure, a critical aspect of health and safety in many environments. This diagram illustrates the primary approach, all falling under the umbrella of a noise control. At the forefront of effective noise management or engineering control, you can see the heavy machinery icon. These are measures designed to reduce noise at its source or block the path of sound. Think of quieter machinery, sound barriers, or acoustic enclosures. Engineering controls are generally the most preferred method as they aim to eliminate or significantly reduce the hazard itself. Next, we have administrative control represented by this icon. This involves changes in work practices or policies to limit noise exposure. Examples include scheduling noise operations when fewer people are present, rotating workers through noisy areas to reduce individual exposure times, or establishing quiet zones. Often, a combination approach is most effective, that is, engineering and administrative control can be used together to achieve optimal noise reduction. Finally, when engineering and administrative controls are not sufficient or reasonably practicable to reduce noise to safe level, we turn to other effective measures. When tackling any noise issues, a clear understanding of the problem is paramount. This forms the bedrock of an effective control strategy. To adequately define the noise problem and lay a solid foundation for our control measures, several critical factors must be carefully considered. First, we need to identify the type of noise. Is it continuous, intermittent, impulsive, or perhaps combination? Different types of noise often require different control approaches. Next, understanding the noise level and temporal pattern is crucial. How loud is the noise? Does its intensity fluctuate over time or is it constant? Are there specific time when it was? This helps us quantify the exposure. We also need to analyze the frequency distribution of the noise. Is it high frequency, low frequency, or broadband? The frequency content influences how the noise is perceived, how it travels, and what material will be most effective in controlling it. Identifying the noise sources is a key step, where it is originating, what is the power, and which direction it is primarily radiating. Pinpointing the source allows for targeted interventions. Then, we must consider noise propagation pathway. How is the sound traveling from the source to the receiver? Is it primarily airborne or is it moving through structure of the building? Understanding these pathways help us to interpret them. Finally, room acoustics, including factors like reverberation, play a significant role. How does the sound behave within the space? A room with hard, effective surfaces will have more reverberations, potentially amplifying the noise problem, whereas a room with absorptive surfaces can help dampen it. In this slide, we are delved into the hierarchy of noise control measures. This is a prioritized approach to manage noise, guiding us to select the most effective and reliable methods. At the top of the hierarchy, our most preferred approach is engineering control. As you can see, these are modifications to the plant, process, or equipment designed to minimize exposure to excessive noise. The goal here is to either suppress the noise at its source, reduce the overall level of exposure, or limit the area affected by the noise. Common types of engineering controls include absorption, insulation, dampers, silencers, and vibration isolations. It is critical that specific engineering control measures chosen are assessed for the suitability, use, effectiveness, and the maintenance requirements of the equipment. And if needed, employers should always consult with acoustic experts or noise control suppliers. If engineering controls are insufficient or feasible to reduce noise exposure adequately, we then move to the next level, that is administrative control. These measures focus on how work is organized. The aim here is to reduce either the number of workers exposed to the noise or the duration of their exposure. Think of things like changing shift patterns, rotating jobs, creating quiet errands. Administrative control should be considered when it is not possible to reduce noise exposure sufficiently through engineering means alone. Finally, at the end, it is other controls. This come into play if it is not practicable to reduce excessive noise through either engineering or administrative controls. In such situations, the employer must take other effective measures, and this primarily includes the use of personal hearing protectors such as earplug or earmuff. It is important to remember that relying on personal protective equipment is considered the last line of defense, used when other more robust control measures cannot achieve the desired noise reduction. We delve into hierarchy of noise control measures in that this is a prioritized approach of managing the noise. We studied about the engineering control, which is the preferred one. There are modifications to the plant, process, or equipment designed to minimize exposure to excessive noise. The goal here is to either suppress the noise at its source, reduce the overall level of exposure, or limit the area affected by the noise. And in engineering controls, we are having the use of the reduction of noise at the source that we already discussed, like absorbers, silencers, all those things. And we have to prevent and reduce the propagation. In relentless pursuit of quieter workplaces, one powerful strategy emerges: buy quiet. Instead of battling noise after it is generated, why not choose equipment designed from the outset to operate silently? Take this new generation genset for example. At the right, a built-in silencer ensures its operation stays below a remarkably low 85 decibels. This proactive approach minimizes noise pollution right from the start, creating a more comfortable and productive environment. The bike quiet philosophy extends beyond large machinery. Consider even seemingly small components. We see the impact of material selection on noise generation. A steel cap produces a notable sound on impact. Now, observe the same impact on a rubber cap, a dead, highly internally damped material. A difference is striking. Sound is significantly reduced. By strategically helping replacing acoustically live materials with their quieter counterparts, we can subtly yet effectively dampen overall noise levels. Principle also applies to everyday tools and equipment as well. This utility cart equipped with rubber type wheels glides with far less noise than one with traditional odd wheels. Every choice from the largest machine to the smallest wheel presents an opportunity to buy quiet and contribute to a less noisy and more harmonious workplace. When it comes to tackling noise in any environment, a systematic approach is key. Noise control efforts should always follow a well defined hierarchy of control strategies. This hierarchy progresses. First, we address the source of the noise. If we can't eliminate the noise at its origin, we then look at modifying the path it travels. And finally, as a last resort, we focus on protecting the receiver, that is, individuals exposed to the noise. Most effective way to reduce noise is to tackle the problem directly at the source. This might involve using quieter machinery, implementing better maintenance practices to reduce the vibrations, or even redesigning the processes to inherently generate less noise. If controlling the noise at the source this is entirely feasible, the next step is to modify the path the sound takes. This can involve installing barriers to block sound waves, enclosing noisy equipment to contain the sound, or applying sound absorbent material to reduce reflections and reverberations. Finally, if noise cannot be adequately controlled at the source or along the path, the focus shifts to protecting the receiver. This can be achieved by physically removing individuals from the noisy area, limiting their exposure time, or providing them with hearing protective devices commonly known as HPDs, such as earplug or earmuff. We have discussed the hierarchy of noise control, addressing the source, modifying the path, and protecting the receiver. Where the robotic arm represents a potential noise source, notice how sound waves depicted by these lines radiate outwards in all directions. As the sound travels along its path, we have opportunities for interventions. We can see example of blocking a barrier which can deflecting the direct sound waves. Additionally, absorption can occur as sound waves interact with surfaces, reducing their intensity. Finally, sound wave reach the receiver. In this case, a person working at a desk, if noise control measure at the source or along the path are insufficient, we must focus on protecting the individual. At the source, we might modify the equipment to run quietly, redesign the process to eliminate noisy steps, or even relocate the noisy machinery to a less sensitive area. In the path, to control it, we can use enclosures to contain the sound, apply absorption materials to walls and ceilings to reduce reflections, or blocking barriers between sound and the receivers. And for the receiver, we again consider enclosures, perhaps a quiet workstation. We can use absorption within the workspace to reduce reflected noise. And as the last resort, we might need to relocate the individual to a quieter environment or provide personal hearing protection. Effective noise control isn't a one-time fix, it is an ongoing process. Here, this cyclic diagram illustrates how to manage and minimizing the noise in any environment. The cycle begins with proper design and selection. By carefully choosing equipment and designing workplaces with noise reduction in mind from the outset, we can prevent many noise issues before they can arise. Next comes proper maintenance. Regularly inspecting and maintaining equipment ensures it operates as intended and doesn't generate necessary noise due to wear and tear or malfunctions. Another key strategy is the reduction of impact forces. Many industrial and even everyday noises are generated by impact. Implementing cushioning, dampening materials, or modifying processes to minimize force contact can significantly reduce noise levels. Vibration damping plays a crucial role in noise control. Vibrations in machinery and structures can radiate as sound. By using damping materials and techniques, we can absorb these vibrations and prevent them from becoming airborne noises. The use of enclosure is a common and effective way to control noise along its path. By physically enclosing noisy equipment or processes, we can contain the sound and prevent it from spreading. Finally, the cycle includes modification or replacement. If existing equipment is inherently noisy, despite maintenance and other efforts, it may be necessary to modify it with quieter components or replace it entirely with a quieter alternative. This cyclic approach emphasizes that noise control is not static. It requires continuous attention from the initial design and selection of equipment through ongoing maintenance, implementing noise reduction techniques, and even considering modification or replacement when it is necessary. When tackling noise issues, most effective and preferred method falls under the umbrella of engineering control, specifically addressing the noise directly at its source. Implementing engineering control at the source is generally considered the most robust and long lasting solution. To do this effectively, a thorough understanding of how the machine or process operates is crucial. This knowledge allows us to pinpoint where noise is generated and explore potential solutions at that very point. One fundamental approach is to entirely eliminate the noisy machine or process if possible. Alternatively, we can replace it with a quieter operation that still achieves same or better efficiency. These proactive substitutions can drastically reduce noise output. Another key strategy involves directly replacing noisy machinery with newer equipment specifically designed to operate at significantly lower noise levels. This bi-quiet approach integrates noise reduction into the equipment itself. We have established that addressing noise at its origin is the most effective strategy. Let's delve into more specific engineering solutions that target the source directly. One crucial approach involves correcting the specific noise source through minor design changes. Even seemingly small modification to a machine design can have a significant impact on its noise output. Maintaining a high standard of plant and equipment maintenance is paramount. Well-maintained machinery operates more smoothly and generates less unwanted noise. Regular check, lubrication, and timely repairs are essential for noise control. Instead of viewing the entire machine as a single noise source, it's often more effective to correct the specific machine elements that are the primary cause of the noise. This localized approach allows for targeted solution. Another valuable technique to separate the noisy elements is that don't need to be integral part of the basic machine. By physically isolating these components, we can prevent the noise from propagating throughout the equipment and the surrounding environment. Finally, it is very important to isolate vibrating machining parts to minimize noise generated by a vibrating panels or guards. Using vibrating isolators, dampening materials, or modifying the mounting structure can prevent these vibrations from radiating as audible noise. We have established that addressing noise at its origin is the most effective strategy. Let's delve into more specific engineering control solutions that target the source directly. One crucial approach involves correcting the specific noise through minor design changes. Even small modification to a machine design can impact on significant noise reduction. Maintaining a high standard of plant and equipment maintenance is paramount. Well-maintained machinery operates more smoothly and generates less unwanted noise. Regular check, lubrication, and timely repair are essential for noise control. Instead of viewing the entire machine as a single noise source, it is often more effective to correct the specific machine elements that are the primary cause of the noise. Another valuable technique is to separate noisy elements that don't need to be integral part of the basic machine. By physically isolating these components, we can prevent the noise from propagating throughout the equipment and the surrounding environment. Finally, it is vital to isolate vibrating machine parts to minimize noise generated by vibrating panels or guards. Using vibration isolators, damping materials, or modifying the mounting structures can prevent these vibrations from radiating as a audible noise. Beyond making engineering changes to machinery and its components, another powerful way to control noise is by modifying the process themselves. Often, the very way of task can significantly impact the amount of noise generated. By carefully examining and adjusting our work process, we can discover inherently quieter methods. A key aspect of process modification is to actively seek out and implement alternative techniques that naturally produce less noise. This might involve using different tools, changing the sequence of operations, or adopting entirely new methodologies. In this diagram, we can see instead of using a hammer to bend a piece of material, a process that generates significant impact noise. Here, we are showing a method of bending using a tool that applies steady pressure. This alternative process achieves the same result with considerably less noise. Consider these two types of containers. Top container with all welded panels is more likely to vibrate and generate noise when moved or when items are placed inside. The, Here, the second container constructed with a tube frame, gap, and distance pieces for fixing the panels introduces damping and reduces the potential for large resonant vibration and thus less noise. Choosing the later design, this one, during the process of material handling can be a form of engineering control at the source. We have explored modifying the machinery and process. Now consider how engineering control at the source can be applied to material handling also. Material handling process in particular offer significant opportunities for noise reduction. By carefully analyzing how materials are handled and transported, we can implement changes to minimize impact and shock. These diagrams illustrate practical example of engineering control in material handling, both saying a hopper designed to receive materials from a conveyor belt. The top diagram shows a hopper lined with heavy-duty abrasion-resistant inner skin. While durable, this rigid lining can generate significant noise when materials impact it. The second diagram showcases a modified design approach, incorporating an impact-absorbing damping construction. Notice the addition of resilient damping layer beneath the heavy-duty abrasion-resistant inner skin. This extra layer acts as a cushion, absorbing the energy of falling material and significantly reducing the impact noise transmitted to the hopper walls. When engineering control at the source are not entirely sufficient or a supplementary measure, we turn our attention to manage noise along its path from the source to receiver. There are several key strategies for controlling noise at the path. This diagram illustrates three important categories: barriers, shields, and observative lining. Often combination of these techniques provides most effective noise reductions. Barriers are physical obstructions placed between noise source and the receiver. This can be walls, partitions, or even strategically placed equipment. The principle is simple: to block the direct path of the sound wave and force them to travel longer, less direct route, thereby reducing their intensity at the receiver. Shields are similar to barriers but often more localized and directly associated with the noise source. Think of a machine guard or enclosure that partially or fully surround the noisy equipment. Shield aimed to contain the sound energy closer to the source and prevent it from radiating freely into the surrounding area. Observative lining involves applying the sound absorbing material to surfaces within the environment such as wall, ceiling, and even the interior of enclosures. These materials, often made of porous or fibrous, which is helped to reduce noise by absorbing sound energy rather than reflecting it. This minimizes reverberation and buildup of sound intensity within a space. It is important to note that these strategies also work in conjunction. For instance, barrier might be lined with absorbative material. By thoughtfully implementing barrier shield and absorbative lining, we can effectively control the path that noise travels and create the quieter environments. Having explored controlled noise at its source, we now turn our attention to engineering control at the transmission path. This involves modifying the environment between the noise source and the receiver to reduce the amount of sound that reaches the listener. Engineering controls along the noise transmission path include several key strategies. One approach is isolating the noise emitting object within the enclosure or placing them in a separate room. This physical barrier impedes the direct travel of sound wave. Another tactic involves building away from the largest number of employees, increasing the distance between the source and the receivers, which naturally reduces the sound intensity. Further, acoustically treating the area to reduce the noise to the lowest practical level is crucial. This can involve using sound absorbing materials on walls, ceilings to minimize reflections and reverberations. Alternately, instead of solely focusing on enclosing the noise source, it may be more practical to protect the employee directly. This can be achieved through the design of soundproof room or the use of sound reducing enclosure for the employees. And all these diagrams clearly explains how what we are going to do to control it by using acoustic panel barrier to block the direct sound wave from reaching the person, and this middle diagram demonstrates indirect path control. Here absorbing material is applied to surfaces, reducing sound reflections and reverberations that would otherwise contribute to the overall noise level. And the bottom diagram illustrates receiver control, where a personal enclosure and headset are used to protect the individual from the noise. We continue our exploration of controlling noise along its path, focusing on practical applications within a workplace setting like this. This diagram illustrates two key strategies: utilizing sound observation and implementing physical barriers. The first scenario, we see a noisy machine emitting sound waves. Notice how some sound travels directly to the worker in a quieter area, while other sound waves reflect off the ceiling. This reflected sound can significantly contribute to the overall noise level in the workplace. To mitigate this, sound absorbing materials has been added to the roof. This material, indicated by label shown absorption acoustic, soaks up a significant portion of the reflected sound energy. The correct use of absorption on surfaces like the roof effectively reduces the reflected noise reaching the quieter work area, improving the overall acoustic environment. The second scenario demonstrates an alternative approach. Here, a physical barrier labeled as partition has been placed between the noisy machine and the quieter work area. This partition effectively blocks the direct path of the sound wave emanating from the machine, preventing them from reaching the worker in the adjacent area. While some sound might still travel over or around the partition, intensity reaching the quieter zone is significantly reduced. We continue our discussion on managing noise along its transmission path. This slide outlines the key principles to observe when implementing engineering control between noise source and the receiver. The first principle highlights that distance is often cheapest solution. Simply increasing the distance between noise source and the receiver can significantly reduce the sound intensity. However, it is important to note that distance alone may not be effective in highly reverberant environment where sound reflects strongly off surfaces. The next principle emphasizes the use of noise barriers. Erecting a physical barrier between noise source and receiver can effectively block the direct path of sound. Once a noise barrier is in place, further treatment may be necessary. This third principle suggests that adding absorbing material to the surfaces of the barrier facing the noise can further enhance its effectiveness by reducing sound reflections off the barriers itself. When designing falls and machine enclosures for noise control, it is crucial to minimize resonance. Resonance can amplify sound energy at specific frequencies, potentially transmitting noise to the protected area. Therefore, design considerations should aim to avoid or dampen the resonant frequencies. Finally, the last principle focuses on the environment where the noise is generated. It advises to reduce reverberation of the room by introducing acoustically absorbent material. By minimizing reflections within the source room, we can reduce the overall sound level and the amount of noise transmitted along the path. These principles provide a framework for effectively implementing engineering controls along the noise transmission path. We continue our exploration of managing noise along its path. The image provides specific examples how we can apply engineering control to reduce the noise as it travels from the source. The These two diagrams illustrate the principle that increasing the distance between the source and the surrounding environment can reduce the noise intensity and reducing the curve. On the left, we see a regular causing turbulence in a airstream, leading to sound emission at a short distance. On the right, by simply increasing the distance after the regulator, the sound has dissipated more before reaching the opening. Bottom, these two diagrams demonstrate how managing the airflow reduces the noise. Diagram on the left shows sharp corner in a duct causing significant turbulence near a fan which generate the noise. In contrast, the diagram on the right illustrates using a smooth corner in the ductwork minimizes turbulence, resulting in less noise generated and transmitted. These are the examples specifically for controlling the noise by distance and carefully designing the airflow path to reduce turbulence. By strategically increasing the distance sound has to travel and minimize the disruptions in the medium through which it travels, such as air, we can effectively reduce the noise level reaching the sensitive areas. These are practical applications of engineering control focused on modifying the transmission path. We have discussed various strategies for noise control and they all fall within the framework of source path receiver model. This model helps us categorize where we can intervene to reduce noise effectively. The treatment strategies we have explored primarily utilize engineering controls, meaning we modify the environment or equipment to reduce the noise. This table provides a general idea of typical noise control reduction as we might expect when applying engineering controls at different stages of source path receiver model. Keep in mind that these are approximate ranges and actual reductions can vary significantly depending on the specific situation and effectiveness of the implemented controls. Addressing the noise directly at the source can typically yield noise reduction in the range of 6 to 8 decibels. While this might seem modest compared to other strategies, reducing noise at the source is often most fundamental and can have a ripple effect, lessening the need for extensive control along the path or the receiver. Intervening along the direct path between the source and the receiver, for example by using barriers, can achieve more significant noise reduction ranging from 10 to 25 decibel and potentially even higher dependency on the barrier effectiveness. Finally, implementing control at the receiver, such as soundproof enclosures or personal hearing protection, can also provide substantial noise reduction, again in the range of 10 to 25 decibel. However, we have discussed focusing on the source and the path is generally preferred over slowly relying on receiver based controls. Understanding the torque, that is, which is going to be the main important type of noise reduction, we can choose the each stage of the source path receiver model, which in turn help us prioritize our noise control efforts and choose the most effective strategies for a given situation. Often, a combination of approaches targeting the source, path, and receiver provide the most comprehensive and satisfactory noise reduction. And that brings us to the conclusion of this unit on noise control strategies. Thank you for your attention and taking the time to learn the various methods, principles involved in creating quieter and more comfortable environments. We hope this presentation has provided you with valuable insights into the understanding, controlling, and ultimately reducing unwanted noise in different settings. I, Dr. C. Sindhamarakannan, signing off with this in the unit 4, that is noise control.